In the last segment, we talked about various kinds of stresses that generally exist, like normal stress, shear stress, the bearing stress, etc. It was a preliminary discussion on stresses. We will discuss in detail how to define a stress formally. But then, as I had already told you, that we will get into the concepts of axial loading. Okay, and then the setup for this is something like this. For example, you have a a prismatic bar like that, which is fixed to the roof maybe, and then you are applying a force F here. So to so this is the simplest example where we can visualize the concepts of normal stress or the axial loading. Okay, and then but then there are some assumptions which need to be very careful about, and those are like this. First is this rod which we have drawn here must be a prismatic bar. What I mean by that is a cross section which has been extruded in a straight line, and that is under this force. Okay, and that's why it's called the prismatic bar, because if you remember, you had always used, for example, a triangle. If you extrude, so you will get a prism, right? Generally we call that as prism, but precisely it should have been called triangular prism. You can have a rectangular prism, which generally we call a cuboid. Okay, so something like that, and there is no restriction on the cross section which we try to extrude, and so similarly in this case there is no restriction on the shape of the cross section of this bar, but whatever it is just extruded. Means the cross section has been moved perpendicular to its own area by a certain distance, and that distance is generally more considerably more than any of the dimensions of the area. So it's not like a cube. Means if you take a square and if you extrude this much, so it will become a cube, isn't it? So it's not like that. So but then it's a long prismatic bar. So that's the setup, and then so that's the first assumption, and then you are applying a force at one of the end. The other end is fixed. Now here what we are saying is this force you should try to apply as uniformly as possible on this area of cross section, because our requirement is that if we see the stress anywhere in the cross section, we want it to be as uniform as possible. For example, let me take an area, some area of cross section, say like this. Okay, so this I am expanding here. Say suppose this is the area of cross section. Now the stress at every point we want it to be, say, uniform, and that will happen if we try to put this force or distribute this force as uniformly as possible on this end. If we don't do that, then also it's possible to consider this axial loading as a uniform stress condition, provided we are not talking about cross sections which are very near to this end or this end, the end which is connected to the ceiling or the end at which we are applying the force. Okay, what I mean is, suppose you are applying a concentrated force and not a distributed one, uniformly distributed one, still if you come far away from this point of application of force, and if you are still far away from the other end, then the stress which exists here will be almost uniform. Okay, because here if for a concentrated load the stress will be something like this. It's a distributed one, means non-uniformly distributed, but as soon as you come closer, far away, so if you go here, maybe it will be like that, then it will be like that, and then if you go farther, it will be more flat. So that is one of the major assumption under which we will develop all the theory or the formulations which in this section. They are under this assumption that the stress is uniform along any cross section. Okay. And yeah, so with that assumption in place, okay, so I'll remove these things and then I'll erase this, sorry. Now under such condition, what has been observed is, let's define the sigma normal stress to be the force per unit area. I think I'll increase the font size a bit. Say F over A. So this is area A. Okay. So this force which is normal to this area of cross section. So if you divide, you will get the normal stress. And suppose because of this force, this rod got elongated to say this kind of a place. Okay. Now suppose this part is some delta length, and this was initially say L length. Okay. Then we define the strain. I am sure that you have studied this. Okay. In the strain, you will define as the change in length over the original length. Okay. So this is what you define from the geometry of what has happened. Okay. So you applied the force, it got elongated, you measured the change in length, divided by the original length, you define strain, and you know the area, okay, and you know the force, so you divide force over area and you get the stress. But then these are not independent properties, so they are related with respect to the material. We have the experience that a strong material, when we think strong material, so if we apply a force, it does not elongate more, but a rubber band, it gets elongated very easily. So that means it is the material which decides the relationship between them, and all of you know that the Young's modulus, now we will define this with the term, represent this with the term E, not Y generally. So that will be say this sigma over this epsilon. Okay. Now, so that will be what? Your F over A over delta over L. Okay. So that means you will get say F L over delta A. Or from this, generally it is not written in this form, but you write as, you know, the elongation that is caused is your F L over E A. Okay. So that's so these are some of the relationships which you should be aware of also, and you should always keep them in mind. Okay. So that means if you look at this elongation which is caused due to the force, so here you look at this. So this is an external source. Now these and these are geometrical, and this is a material property. Okay. So the elongation which is caused is a function of three kinds of things. One is external factor, the load, then the geometry, and the material property. And sometimes what's done is, this is written in terms of in a way like this. I'll change the color, maybe say like this. F over delta, you will get say EA over L, right? Now, do you recognize this form? Because this is something like force that you require or the effort that you need to have a particular or unit elongation, right? F over delta. So, it is like the stiffness of a spring. So, a rod can be thought of as a spring whose stiffness depends on E, A and L, and obviously the stronger a material, okay, I am using the word loosely, so that means the Young's modulus, if it is more, then the stiffness will be more. If you increase the area, obviously keeping all the other things same, the stiffness will increase, and if you have a longer rod, the stiffness will be reduced. So, that is what is conveyed by this, and then once you have this stiffness formula, you can actually use all your knowledge which you had acquired of connecting them springs in series, connecting springs in parallel, all those things you can actually use once we go to solve difficult problems, when we connect various kinds of rods and annular cylinders, all those things under axial loading. You can actually use the concepts of stiffness, the same way use the concept of stiffness of spring. Yeah. Now, here I want to make one point clear, that see, we defined this, Young's modulus to be the ratio of the stress to strain, but when we did that, it's not in a way not a correct statement without any constraints. Okay, so this is an experimental fact which is valid under certain conditions. So what those conditions are, I'll just take 5 minutes to talk about that. See, for example, any material like say steel you take, and then let us say we conduct experiment and we pull it by a force, some amount of force, and we measure the elongation, we divide by its original length, and we will get the strain, and we will plot the strain on this side and we will plot the stress on this side. Okay, and then what will happen is, for materials like steel, you will get something like this, a curve something like that. It's a very representative curve. Okay, and then there are certain important points on these curves which are to be noted. For example, up to certain point here, say I'll name it A, the stress will be exactly proportional to the strain, okay, and the proportionality constant being the Young's modulus. Okay, the ratio, the slope of stress to strain will give you the Young's modulus, and in this zone, that is until you get to this strain value, so you can say that the Young's modulus is a constant, but then after a certain point, that A, it will no longer be proportional, slightly it will start reducing, the slope will be reduced, and you will reach a point like here, say B, which is generally called the yield point or the upper yield point. Okay, and then slightly it will reduce, this dip is a very small dip. Okay, and this is sometimes called the lower yield point, and this is the zone of yielding. Okay, and then some phenomena known as strain hardening. Okay, because of the strain in the material, the material gets hardened in a way, and then again the stiffness in a way increases, the Young's modulus, okay, as compared to this. So here you see, even if you are not increasing the load in a way, the it's getting elongated. That means the material has yielded, means it has surrendered itself, and without even increasing of stress, you are getting an increase of strain. Now this is the point where you call the ultimate stress. That's the maximum stress which the material can withstand, and then it will go to a point where this point E, you can say that it's fractured. Okay, so from there it will just break. Okay, so this is the breaking stress or the fracture stress. This is the ultimate stress. These are upper and lower yield points. This is the proportionality limit. Okay, A is called the proportionality limit. I think I forgot to tell the name for that. And then this is more or less for many materials, engineering materials, the shape will be like this. But some of the other materials, like say aluminum, it will not behave exactly like this. Maybe it will behave something like this. Okay, and some of the brittle materials, they behave very differently. They don't have such phenomena, so they will just go like that and fail somewhere. Okay, so these are, but for this course and then the subject which we are dealing with, we are not bothered about anything which is happening so complex way. Okay, we will restrict ourselves to this zone where the stress is completely proportional to the strain. Okay, and the relationship between them is given by the Young's modulus, which is given by E and which is given by the stress over the strain. So this, I just told that you should know that this Young's modulus is not a constant forever. It depends on actually the stress and the strain. Basically the strain, the more you elongate, it doesn't remain constant, it changes. So like that. But our focus will be in this zone where, and then this zone is what? That means it's very, the strain is very small. And if you remember, I had told you that we are going to deal with materials or the situations where they are little bit flexible. They are not flexible, means when I said that, means when I took this ruler, so this much bend is fine, but I am not bending it to make a coil out of it. So those are called large deflections, and many other things happen. So such are the deflections which are happening there. Okay, so we are concerned with very small deflections under which these conditions are valid. Okay, so that is the story. But then, okay, before we leave this topic, what I would like to do is, I'll give you a canonical configuration. That means pure axial loading. When we say this configuration should always come to your mind. Okay, and then all the formula that you derived, that is of the displacement, mean the elongation, the strain, then the stiffness, anything that we derived now till now is valid till this configuration is valid. Okay, and this is like this. So you are applying a force here, the same force here. The area of cross section remains constant. Okay, in the prismatic extrusion process, you didn't increase the area of the cross section. Okay, so that's the major assumption, and yes, so that's it. So there is a bar of uniform cross section. At the two ends, you are applying the equal and opposite force F, and the material property E is the proportionality constant between the stress and strain. So these are the whole story, and from there we can, okay, so these are the two things which I would like to write there. Maybe so del is F L over AEL, right? And then your F over delta is A E over L. Okay. So, this is a setup which you should keep in your mind, which I will be referring to as the canonical form. Okay. And if any of the assumption is not valid in a particular condition, you can't use these forms directly. For example, if the area of cross section is changing gradually, so you cannot just use this. Okay. I'll put it here. See, this is it's the area A and the length L. Okay. So, now any of the assumptions, if it is violated, you cannot use this, but then the solution to that problem is you have to go to a small length where you can assume that this condition again prevails, and then for that small segment you can again apply all these things, and then the usual way you can integrate it to get the full solution. So, we will see such problems, but that is what, so in this segment what we saw is we defined what the axial loading condition is, what are the assumptions involved, the material property characteristics which are required for this discussion to be valid, and then this is the canonical configuration which we will always use in situations where more complex conditions will arrive, and then we will have to break those problems into these canonical segments, so that we can apply the formula which we have derived for those small segments. Okay, see you in the next segment with some more discussion on this.